So hi again. After the general introduction, now let's look at how the neural networks, the main subject of our whole course, are constructed. And here again, we will start from the complete basics and talk about the little parts, the neurons, the forward pass, the back propagation, and then at the very end, in the very last slides, we will talk about how you can make such a network bigger. Right, so to start from the neurons, well, it's a neural network. A neuron in this case is defined or could be defined as a function whose output is constructed by applying an activation function to a weighted sum of its inputs. So here is the formula on the screen, perhaps that's easier to parse. So the simplest neural network that one can think of then is a combination of three neurons like this. So you have two inputs, x1 and x2, and then out of those it constructs a weighted sum. And yeah, here we just forgo the activation function. Let's look at the activation functions later. But for now, let's imagine it's all linear and there is no real activation happening. So let's think of what we could actually do with a model like this. So suppose we acquired some measurements and we suspect that this is actually a weighted sum of the inputs. So I'm not saying you would ever actually do it like this in the real world to do a linear fit, but suppose you wanted to, just as an educational example of how one could do it with a little neural network like this. So how do we actually find the parameters of the model? So to do that, we first have to define the so-called loss function or the error function, which will estimate how far we are from the true value that we want the model to estimate. Well, the popular choice here is the mean squared error, which is defined as usual. T is the target true value. Let's take this one and see what we can do with it. So we start by initializing the weights randomly. We compute the so-called forward pass for a single training point. So the forward pass is the output of the complete network, given the current parameter values. In our case, this is, well, you take a training point, x1 and x2, and then you compute the weighted sum with the current parameter weights. And then we see with the loss function how far this output is from the true value. So if you're still in the beginning of the training process and your weights have been initialized randomly, chances are you're still quite far. So what can you do about this? How can we improve? Remember that this was the formula for the loss function. And now if you look at this loss as a function of the weights for a given point, so for a given x1, x2, the training point, you can see that, well, the function as we have it now looks like something like this, right? So it's sort of a parabola. Actually, it is a real parabola here. And our current state would be somewhere here. So the question would be, how do we change the weight W so that the error E becomes smaller? And well, we know how to do that. We follow the gradient to the minimum. And let's do just that. So how would we update the weights? We find the gradient of the loss. And then, well, we have to decide beforehand on a certain parameter called the learning rate, which just determines how far we step along the gradient, right? So how much do we actually update now that we know the direction in which to go. And then we update the weights by adding the learning rate multiplied by the gradient. So let's just do it by hand for our tiny little network. And we initialize the weights to say 0.1 and 0.1 and take the same 0.1 as the learning rate, right? And we take our first training point as 0 and 1. And well, we just learned the simple average. So here the target would be 0.5, right? So we can compute the value of the loss. We can then compute the value of the gradient. And from there on, we can also update the weights. So the first weight is not updated. The second weight, we would update from 0.1 to 0.14. So you see, we're getting closer. So then we take the next training point. We already have the new weights, 0.1, 0.14, same learning rate as before, although you can change it. And yeah, let's take 1 and 1, and then the average would be 1, right? So we can compute the loss, we compute the gradient, we update both points. Now we are standing at the weight 1 at 0.76 and the other one at 0.21. Right? And so you keep going like this over the iterations, and eventually it would actually converge to the correct weights of 0.5, 0.5. So if you wanted to do it in Python and not just do it manually, thinking up the training examples as you go, it's actually not much code, right? So you see here, I have it in 28 lines, including the printing. So I could make it in a Jupyter notebook, but I thought if you actually want to reproduce it in Python, it's not much. You can also do it from scratch. So what do the parameters actually mean? What does the learning rate really control? So we can look at the evolution of the weights as we go through the iterations with the different learning rate, right? So this is the learning rate equals 1, and the one that I used in the code. And well, you can see that they nicely converge to 0.5, oscillating quite a lot in the beginning though. So if you make this value even higher, it will oscillate more. Because remember that this value actually controls how much we step in the direction of the gradient. So if we step too much, we overshoot, and then we have to step back and then forward again and then back again. And so making it too big is not a good idea. On the other hand, making it too small is also not a good idea, because then you can only, and you need a lot of iterations to actually get there. And so here we have unlimited number of iterations, but in 100, it didn't really get very close. So it's going in the right direction, but it's updating itself really, really slowly. So you have to find some kind of a middle ground. And like I said in the earlier example, we don't really have to keep the same learning rate all the time. And usually what people do when training the big networks is that you start from a fairly big learning rate so that you quickly get somewhere, and then you gradually decrease it so that in the end you just do the fine scale refinement, so to speak, of the position of the minimum. But here, in a small problem like that, we probably wouldn't bother with this. Also, many people still use the constant learning rates. So this is this kind of your mileage may vary territory. Okay, so another term that one has to remember is the so-called batch updates, because this is also used for the big networks as well. So you don't have to really update everything after every training example. You can also average it over a certain number of examples, which we would call a batch. So this is more stable in training because, well, the training samples, if you don't have to jerk the gradients and the weights all the time, it could actually work better. Right, so we have seen what the tiny network like that does, but of course this one can only represent linear functions. It can also be shown that even if you add more layers, it could also still only represent linear functions. So to represent something more interesting, we have to add nonlinearity. So remember how we define the neuron as a function that is applying some kind of an activation function to a weighted sum of its inputs. So this actually comes from neuroscience, where the activation function is, well, it's not a function there, but let's say a concentration of certain chemicals that determines when should a neuron fire, right? And here for the neural networks, the main requirements to these functions are that, well, they should be nonlinear, and they should also be differentiable, because remember that we have to compute the gradients as we backpropagate through the network. So with these two requirements, people have invented a lot of different activation functions, and new ones also get published every year. But the most popular ones come in two shapes. So they're the ones that are like a sigmoid, which you can see on the left, and other ones which are like the ReLU, which you can see on the right. So there are softer versions of the ReLU, there are harder versions of the sigmoid. Now ReLU is probably the more popular options, but yeah, it also depends. But still, I would say that most of the networks now at least start from ReLUs, and then maybe change it to some other activation if needed. Okay, the good thing about ReLUs is that you can see that below 0, it's completely 0, which means that it can also do the activations very sparsely. Okay, so how do we actually construct a bigger network? So there we also have to do some new terminology. The input layer is the one where your data is coming in, right? Then you have the output layer at the very end, and in the middle you have the so-called hidden layers, right? And so what do we do if we have something like that? Also note that here I didn't actually draw all the connections, but all these layers are fully connected. So every input is projecting to every neuron of the next layer. So how do we learn here? It's the same as it was before. So this is the same backpropagation, but now we have to use the chain rule of differentiation to get to the earlier layers of the network. And well, if you don't feel comfortable with it, or if you don't feel like you understand everything, it would perhaps be a good exercise to create a network with one more layer than we had in the previous very simple example. So just add one hidden layer and try to, by hand on paper, compute the gradient on the weights that are in the hidden layer. So that would be an interesting thing to do if you feel like it. If not, just skip directly to the tutorial. Right, to summarize, we have introduced some of the necessary ingredients. So we have the neurons, which pass the weighted sum of inputs through a nonlinearity and then on to the next layer. We have the loss function at the very end, which estimates how far we are from the truth. The forward pass is the current model prediction, so the prediction of the model at its current state. And then we have the update of the weights, which comes from backpropagating the gradients from the last layer and then multiplying it with the learning rate. That's it. In the next part, I think we'll probably talk about the more complex networks.